Good morning or afternoon, guys, depending on when you're watching this video. So today we're going to talk about linear functions and kind of build off of 3.1. This is 3.2. So I'm kind of having some issues with my video camera. So I'm going to put the quote of the week right here. All right, like I said, we're going to do 3.2 linear functions. The objectives for today, we're going to write and evaluate function notation. We're going to graph linear functions, and we're going to interpret functions written in a variety of representations. So the first thing is just something to kind of think about. The flowcharts shows the steps of a math puzzle. Try the puzzle with 6 different integers. Record each number you try and the results. Remember, integers, they don't have decimals, but they could be a negative or a positive number. So an example, let's plug in -2. So I'll plug in -2, I'm thinking of a number. I'm going to multiply that number by 9. So -2 times 9 would be -18. Now I'm going to subtract my original number, so -18 minus -2, which turned into -18 plus 2, which is -16. I divide that by 4, I get -4. All right, another number we could plug in, let's plug in 1. Plug in 1, multiply by 9, I get 9, subtract 1. That's the original number, I get 8. 8 divided by 4 would be 2. Let's try another one. Let's try 3. So I multiply that by 9, I get 27. Subtract 3 would be 24. Divided by 4 would be 6. Let's try, let's do 20. If I do 20, multiply that by 9, I get 180. 180 minus 20 would be 160. 160 divided by 4 would be 40. Okay, let's kind of go back down to a smaller number. Let's try 5. 5 times 9 would be 45. 45 minus 5 would be 40. 40 divided by 4 would be 10. I'll let you guys think of something for the last one. So now it says make a prediction of what the final number will be for any number and explain. Well, hopefully you're kind of seeing a pattern here, right? Whatever I plug in, the result is going to be what? Hopefully you say the result is going to be double the original number. AKA I'm multiplying by 2 to get my result. So this is something that we would call a function. So function notation is a method for writing variables as a function of other variables. The variable y becomes a function of x, meaning the variable x is used to find the value of y. This helps distinguish between different functions, and the relationship between the variables can be used to solve problems and make predictions. The function f is defined in function notation by f of x equals 5x plus 1. So if I say f of x, that means I'm plugging something in for x and I'm going to solve it. Now, if you write it like this, f of x equals 5x plus 1, f of x is the same as saying y equals 5x plus 1. This looks very familiar. We've seen this before. This is slope-intercept form. Function notation just represents a certain line. That way I know which line I'm talking about. So I could say f of x, I could say g of x, I could say c of x, whatever it is. The big thing is that you know whatever it is of x is the same as saying y equals. Okay? So that's function notation. Now what you do with function notation is something like this. This says, what is the value of g of x equals 5x plus 1 when x equals 3? Another way to write this is saying g of 3 equals 5x plus 1. So what you're doing here is I'm plugging 3 in for my x, and I'm going to solve it. So I plug in 3 in for my x and solve. G of 3 equals 5 times 3 plus 1. G of 3 equals 15 plus 1. G of 3 equals 16. So whenever I plug in 3 for my x, aka g of 3, I get 16. So my input is 3, my output is 16. And that's like a coordinate. X is 3, y is 16. So I want you to go ahead and try the next two. I'm plugging in 4 for my x. So again, another way to write it, g of 4 equals negative 2x minus 3. So now I want you to solve it. What am I going to plug in for x? Well, I'm going to plug in 4. Hopefully you got negative 11. So again, if I say plug in something for x, you're plugging in it for every x. You're just not solving the left-hand side because you're plugging in 4 for the x value to figure out what y is. So go ahead and try the next one. Go ahead and rewrite it for you. Hopefully you got 43 whenever you did that. So again, when we say function notation, we're going to plug it in like this or write it like this so you can solve for a number. The next thing is writing an equation. So the cost to make 4 bracelets is shown in the table. How can you determine the cost to make any number of bracelets? Well, if I said 5 or 6 or something like that, it's usually pretty easy because you can find the pattern. And when we talk about patterns, we're talking about change in x and change in y. So notice my x, right, is usually on top, my y is on bottom. What are they doing every single time? Well, they're adding 1. So that's a constant change. That's nice. What are they doing on the bottom? Well, they're adding 15. So every time I go up 1 in x, I go up 15 in y. Guys, if you think about this, your change in y, what are you doing every single time? Over your change in x is your slope, right? Rise over run. So 15 over 1 is my slope, aka my slope is 15. If we're going to write an equation in function notation, right, we need the slope and the y-intercept. Now, what you can do, we have a slope. I can use 117. I have a point now, and I can plug it into point slope form. Let's go ahead and solve it so we can write it in slope intercept form. So I'm going to distribute that 15. I'm going to add 17 to it. All right, this is our equation, but instead of writing y, we can write it as a function and say f of x equals 15x plus 2. Now, no matter how many bracelets I plug in, say it's 20 bracelets, I could find the answer. F of 20 equals 15 times 20 plus 2. Or if it was 22 bracelets or whatever it is. Now you have an equation that you could solve for any amount of bracelets that you were going to sell. Or the cost to make, sorry. So the goal here is to write an equation in function notation. Sometimes the easiest way, like I said, is to find the slope, use a point from your table, and then plug it into point slope form. So let's do one more, and then I'll have you guys try the last one. So again, notice my x is going up by 1 every time. My y by 6.5. So when I solve this, my change in y over my change in x is 6.5 over 1. AKA my slope is 6.5. Now if we use a point, we can write an equation. distribute. Notice my y-intercept is going to be 0, so I don't have to write anything at the end. Now let's write it in the function notation. Let's make this one g of x. All right, so that represents a different line, aka different equation. You can still use f of x, but it's nice to kind of differentiate, use a different letter. So I want you to try b, see if you can get the equation for b. So here's all my work. Hopefully you got h of x equals 3x minus 2. So I found out my slope was 3, and I used the point 1, 1. And I plugged it into point slope form, and then I made it into slope intercept form, and I solved. All right? One of the other big things we're going to do is we're going to graph these. Remember, I told you this is like y equals negative x plus 1. Well, guys, we should hopefully know how to graph that by now. My slope in this equation is negative 1. My y-intercept is a positive 1. So I'm going to graph it just like that. Y-intercept's 1. If my slope's negative 1, I'm going to go down 1, right 1, down 1, right 1, down 1, right 1. You can plot a whole bunch of points. We will stop there. And that's how you would graph f of x equals negative x plus 1. So again, treat this like y equals 3x plus 1. My slope is 3. My y-intercept is 1. You can also think about your slope as 3 over 1. So I'm going to graph my y-intercept at 1. I'm going to go up 3, 1, 2, 3, right 1. 1, 2, 3, right 1. Or I can go down 3, left 1. There you go. So that should be nothing new. It's just written in a different order, right? Just written in a different form. Not a new concept, just written differently. So now this one says, Tamika records the outside temperature at 6 a.m. The temperature increases by 2 degrees Fahrenheit every hour for the next 6 hours. If the temperature continues to increase at the same rate, what will the temperature be at 2 p.m.? Well, guys, let's think about it. Can we write an equation for this? Hopefully we can, right? So it increases by 2 degrees Fahrenheit every hour for the next 6 hours. If the temperature continues to increase at the same rate, what will the temperature be at 2 p.m.? Well, we're going up by 2 degrees every hour. So my slope is 2 degrees every hour, aka my slope is 2. Now let's figure out where we started. Where we started is over here in the graph. My y-intercept is negative 3. So if I wrote an equation, it could look like f of x equals 2x minus 3. Now, how long is it from 6 a.m. to 2 p.m.? Well, 6 to 7 would be 1, 7 to 8 would be 2 hours, 8 to 9 would be 3 hours, 9 to 10 would be 4 hours, 10 to 11 would be 5, 11 to noon would be 6, noon to 1 would be 7, 1 to 2 would be 8. So I'm looking at 8 hours here. So what am I going to plug in for x? Well, I'm going to plug in 8. So I'm going to find f of 8. So if I wait 8 hours, hopefully the temperature is 13 degrees Fahrenheit. So the next question, it says, does using a linear function realistically represent the temperature for the domain of 0 less than x less than 24? Well, if you think about it, if I wrote it in a linear equation, that means it's going to always increase by 2. Does the temperature always increase by 2 the whole day? Hopefully you're sitting there saying no, because if you think about temperature, yeah, it increases throughout most of the day until about, I don't know, 2 or 3 o'clock, and then it starts to go down again, right? So we can't write a linear function because the temperature goes up, but then goes back down. Which is not a linear function. Because a linear function would just be constantly going up. Be a straight line like that if we graph it. Okay? So that's pretty much everything from 3-2. If you have any questions, make sure you're reaching out for extra help to Ms. Sanders or myself. We'd be more than happy to help. Otherwise, homework is Pearson 3.2. Hope you guys have a good day, and we will see you later.